Dear students, in last class we started IIR filters, and there we studied that to design a digital filter we have to first design an analog filter. For that, the desired frequency response of digital filter must be transformed to the desired frequency response of analog filter. After designing an analog filter, we will have to transform the analog filter transfer function into a transfer function of digital filter. So for that reason, it is necessary to have the idea of frequency response of analog filters and digital filters. So in today's class, we will look into the frequency response of analog and digital filters. First, we will take up analog filter frequency responses. As you all know that the filters are mainly of four types, and those filters are low pass filter, high pass filter, band pass filter, and band rejection filter. Now we will take up the frequency response of normalized ideal analog low pass filter. Normalized filter means the maximum magnitude is equal to unity and the minimum magnitude is equal to 0. Here you can see that the frequency response of ideal low pass filter is box like. It looks like a rectangular box. For a low pass filter at 0 frequency, the magnitude is unity, and this magnitude remains constant up to the cutoff frequency omega c. Here omega is the notation used for analog frequency. This omega is also called as capital omega. After omega c and up to infinity, the magnitude is equal to 0. But obtaining such filters is not possible practically. When we design filter and implement it, the frequency response of that filter will be not appearing exactly the frequency response that you are seeing here. It will be something different. And what is that? Now we will see it. Here is normalized magnitude response of practical analog low pass filter. Here you can see the magnitude is not remaining constant between 0 and omega c. that is cutoff frequency. The magnitude is varying or the magnitude is decreasing here. But when the frequency of omega p is crossed, omega p here is called as passband edge frequency. Omega p is called as what? Passband edge frequency. Unit will be for all analog frequencies. For all analog frequencies, unit will be radians per second. We take unit of radians per second. After omega p, you can see that the magnitude decreasing at higher rate comparing to the rate of decrease of magnitude in the frequency range of 0 to omega p. Here the magnitude is decreasing slowly, whereas after omega p the magnitude is decreasing fast. At omega c, that is cutoff frequency, the magnitude is 0.707. After omega c, the drop in magnitude will be still faster comparing to omega p to omega c. Omega p to omega s, the frequency range is called as transition band. 0 to omega p, the frequency range is called pass band. And omega s onwards, the frequency range is called as stop band, where omega s is the stop band edge frequency in radians per second. At omega s, the magnitude is equal to as. As is equal to delta s, where delta s is called as the ripple in the stop band. The ripple in the stop band. So gain will be varying between delta s and 0 in the stop band. Whereas in the pass band, the magnitude is varying between 1 and ap, where ap is equal to 1 minus delta p, and the delta p is called as passband ripple. Now we will consider normalized magnitude response of ideal analog high pass filter. In case of high pass filter, the lower frequency components of input signal are cut off and the higher frequency components are allowed to pass through. Here you can see from 0 to omega c, where omega c is cut off of frequency, the magnitude is equal to 0. And at omega c, the magnitude becomes equal to 1 and it remains constant for all the frequencies above omega c. For frequency omega c to infinity, the range of frequencies is called passband, and the range of frequencies from 0 to omega c is called as stop band. Here also you can see the rectangular shaped magnitude response of ideal filter. Once again, when we design high pass filter, the frequency response will not be looking like this. It will be something different. What is that then? Now we will see. Here also, the magnitude in stop band, transition band and pass band is varying. In the stop band, the ripple is delta s, omega s is stop band edge frequency, omega c is cutoff frequency. At omega c the magnitude is 0.707. Omega p is passband edge frequency in radians per second. Omega p onwards the frequency range is called passband. The frequency range between omega s and omega p is called transition band. From 0 to omega s the frequency range is called stop band. The stop band, the passband ripple is denoted by delta p, and the relation between AP and delta p remains the same, that is AP is equal to 1 minus delta p. Now we will take up normalized magnitude response of ideal analog bandpass filter. The filters used for passing only the frequency components of the input signal in the required range of frequencies is called bandpass filter. So here the frequency, the components of input signal which are having frequencies from omega c1 to omega c2 are allowed to pass through. So for those frequencies the magnitude is 1, and the components of input signal which are having frequencies from 0 to omega c1 and omega c2 to infinity are not allowed to pass through the filter. Therefore, the magnitude for these frequency ranges are equal to 0. Here you can see stop band from 0 frequency to lower cutoff frequency. Here omega c1 is called lower cutoff frequency and omega c2 is called higher cutoff frequency. The range of frequencies from 0 to omega c1 and omega c2 to infinity are called stop band, and the frequency range from omega c1 to omega c2, that is from lower cutoff frequency to upper cutoff frequency, is called passband. Again, like in case of low pass filter and in case of high pass filter, here also the practical filter will not be having such characteristic exactly. Now here you can see the normalized magnitude response of practical analog bandpass filter. Here also in stop band, that is from 0 to omega s1 and omega s2 to infinity, there is a ripple which is called as stop band ripple delta s, and the delta s is equal to as. At two cutoff frequencies, that is lower cutoff frequency omega c1 and upper cutoff frequency omega c2, the magnitude is 0.707. Omega s1 and omega s2 are the two stop band edge frequencies. Omega p1 and omega p2 are the two passband edge frequencies. The range of frequencies from omega p1 to omega p2 is called passband. The range of frequencies from omega s1 to omega p1 and omega p2 to omega S2 is called transition band, whereas the range of frequencies from 0 to omega S1 and omega S2 to infinity is called stop band. In the range of frequencies from omega P1 to omega P2, that is in pass band, the ripple is delta P, and here also delta P and AP are related as AP equal to 1 minus delta P. Now we will take up normalized magnitude response of ideal analog bandstop filter. The bandstop filter is one which does not permit the components of input signal having certain range of frequencies, whereas it allows to pass through it the components of input signal which are having frequency lesser than and more than that range of frequencies. So a bandstop filter has got two pass bands. You can see here is the first pass band and here is the second pass band. The first pass band is from 0 to omega C1, that is lower cutoff frequency, and from omega C2 to infinity, that is upper cutoff frequency. Omega C2 is upper cutoff frequency, omega C1 is lower cutoff frequency. And for two pass bands, the magnitude is equal to 1. The range of frequencies between omega C1 and omega C2 is called stop band, and for the stop band, the magnitude is equal to 0. Now we will see the frequency response of practical analog bandstop filter. In normalized magnitude response of practical analog bandstop filter, we can see the variation in the magnitude in the two pass bands and in the stop band. The ripple in the pass band is denoted by delta P. The ripple in the stop band is denoted by delta S. Magnitude AS is equal to delta S. Magnitude AS, like in previous cases, is nothing but the magnitude at the stop band frequencies. AP, the magnitude at pass band frequencies, is related to delta P by AP is equal to 1 minus delta P. 0 to omega P1 and omega P2 to infinity frequency ranges are called as pass band the frequency ranges from 0 to omega P1 and omega P2 to infinity are called as pass band. The frequency ranges from omega P1 to omega S1 and omega S2 to omega P2 are called as transition band, whereas the frequency range from omega S1 to omega S2 is called as stop band. Now we have to move on to the frequency response of digital filters. We have seen that analog frequency is given by capital omega in radians per second. Digital frequency omega is measured in radians per sample. Frequency response of digital filter is periodic with period of 2 pi radians. The frequency response of digital filters are very much similar to the frequency response of analog filters of same type, and therefore the frequency response of digital filters may be obtained by replacing capital omega by small omega. In frequency response of analog filters, and also by replacing the magnitude of h of j omega by h of e raised to j omega magnitude. So now we will look into the frequency responses of various types of digital filters. Now you can see here normalized magnitude response of ideal digital IIR low pass filter. Here capital omega is replaced by small omega. So cutoff frequency capital omega c will be written here as small omega c, and the magnitude h of j capital omega is here written as magnitude of hd of e raised to j small omega. In normalized magnitude response of practical digital IIR low pass filter also, the notation for analog frequency is replaced by the notation for digital filter, and magnitude h of j capital omega is replaced by magnitude of h of e raised to j small omega. Similarly, the frequency response of all other types of digital filters are obtained, and just see here, it is for ideal high pass filter, it is for practical high pass filter, this is for ideal band pass filter, this is for practical band pass filter, and this frequency response is for ideal band stop filter, and here it is for practical band stop filter. To transform the desired frequency response of digital filter to the frequency response of an analog filter, and to transform the transfer function of designed analog filter into the transfer function of digital filter, we make use of two transformations, namely impulse invariant transformation and bilinear transformation. Impulse invariant transformation in short may be called as IIT, and bilinear transformation in short may be called as BLT. First we will take impulse invariant transformation, that is IIT. In this transformation, the frequency response of analog filter is sampled with very small sampling time in order to preserve frequency response nature when we obtain digital filter. In other words, frequency response of digital filter is obtained by sampling frequency response of analog filter at high frequency of sampling. Now let us understand the impulse invariant transformation technique. For that, let us consider h of t as an impulse response of analog filter. The Laplace transform of the analog impulse response h of t, that means we have to take Laplace transform of h of t, gives the Laplace transform of the analog impulse response h of t gives the transfer function of analog filter. Therefore, transfer function of analog filter h of s equal to h of t. H of s is equal to Laplace transform of h of t. When h of s has n number of distinct poles. It can be expressed as in equation 1 by partial fraction expansion by partial fraction expansion h of s equal to summation from I equal to 1 to n, because there are n number of poles, ai upon s plus pi, that is equal to a1 upon s plus p1. p1 is first pole here. a2 upon s plus p2 plus and so on up to an upon s plus pn. So this is equation 1 now. On taking inverse Laplace transform of equation 1, we get h of t equal to summation I equal to 1 to n ai into e raised to minus pi into t u of t. You know what is u of t? U of t is unit step signal, and this may be written as a1 into e raised to minus p1t u of t plus a2 into e raised to minus p2t into u of t plus and so on up to an into e raised to minus pn t into u of t. Let us call this as now equation 2. Where u of t is continuous time unit step function. Now we have to sample Now we have to sample this equation 2 to get the transfer function of digital filter. For that, let t equal to sampling period h of n equal to impulse response of digital filter. The impulse response of digital filter is obtained by uniformly sampling the impulse response of the analog filter. Therefore, h of n is equal to h of t at t equal to n into t. That is h of n into capital T. Therefore, the impulse response h of n can be obtained from equation 2. By replacing t by n into capital T. Therefore, h of n is equal to h of t at t equal to n into t equal to h of n into t, that is equal to summation I equal to 1 to capital N ai into e raised to minus pi. Here we had small t, now we will write this as small n into capital T into u of nt. That is equal to a1 into e raised to minus p1 nt into u of nt plus a2 into e raised to minus p2 nt into u of nt plus and so on up to an into e raised to minus pn n into t into u of n t. Let us call this as equation 3. On taking Z transform of equation 3, we get h of z equal to Z transform of h of n equal to a1 into 1 upon 1 minus e raised to minus p1 t z raised to minus 1 plus a2 into 1 upon 1 minus e raised to minus p2 t z raised to minus 1 plus and so on up to an into 1 upon 1 minus e raised to minus pn into t into z raised to minus 1. Since we know that z transform of e raised to minus a n into capital T into u of n into capital T is equal to 1 upon 1 minus e raised to minus at into z raised to minus 1. So this standard transformation we are making use here. Now let us call this as equation 4. Now comparing equation 1 and 4, we can say that one upon s plus pi maps to 1 upon 1 minus e raised to minus pi into capital T into z raised to minus 1. Can write here. Arrow mark means is transformed to or is mapped to. Let us call this as fifth equation. By which method? By impulse invariant transformation method. Where capital T is sampling time period. When a discrete time signal is obtained by sampling analog signal, the frequency the frequency spectrum of digital signal will be scaled by a factor of 1 by capital T. Due to this fact, the transfer function obtained by impulse invariant method is amplified by the factor 1 by T. For small values of T, if this amplification is undesirable, then the transfer function obtained by IIT can be multiplied capital T to obtain magnitude normalized transfer function Hn of z. Therefore, Hn of z is equal to capital T into h of z. Dear students, I will stop the class here. In next class, we will learn the relation between analog and digital filter poles in impulse invariant transformation. It is very important to know this relationship because it gives us an idea of stability of the filter. Thank you very much.